Welcome back, and I hope that you're coming from part one of this series. We've covered an introduction of the shear stress formula and showed some real life examples. We've ran through some examples of dealing with built-up sections, or as some may call it, built-up members. In this video, we will go through a step-by-step derivation of the shear stress formula, and then in the following series we will take some worked out examples, actually some hand comps that I've organized. Organized about 3 or 4 good examples that I would like to share with you. So in this formula, tau is equal to VQ over IT, and we went through all the parameters involved in this equation in the video part 1. Now we will go through the derivation of this formula and find out where it came from. I think the main confusion has always been, the question that comes up is, I have always thought that the shear stress is vertical. So, why in the world are we calling it horizontal shear stress or longitudinal shear stress? The simple answer to this, yes, the shear stress is vertical, but a horizontal shear stress is developed in the member due to the varying bending moments along the beam or along the member. And because there are varying bending moment values, there will be a out of balance forces, and the difference in the moments is going to be balanced by the horizontal shear stress. Okay, we will go through it step by step and see how this all works out. Say we have a beam with a length L and a width B and a depth D, which is made up of four planks, say of unbonded wood, and the beam supports, or these planks of wood support some sort of UDL. Okay, there are no glue, no nails, nothing to hold these planks in place other than friction, of course, which depends on the roughness value of the surface, but we will ignore friction in this case. Okay, friction is very important, especially if we're using concrete, but we will discuss this in another video. Now, what do you think will happen if these unbonded planks of wood, when they start sort of bending under these applied loads? Have a think about it. Well, here we will get a flexural deformation. That will be caused in the unbonded planks to slide over. This flexural deformation will cause the unbonded planks to slide over each other. Okay, and they will have this weird looking staggered behavior. Okay, longitudinal shear stress then will develop between the planks. Between each of these planes, you'll get some sort of stresses, longitudinal shear stress, due to bending. And the linear elastic stress and strain analysis can no longer work. It doesn't apply in this case because we don't have a uniform bending. Okay, so this favorite diagram of ours no longer works. We will no longer be able to use this stress is equal to minus my over I and having a uniform compression at the top and tension at the bottom. It doesn't work in unbonded members. And you can see in this little diagram here, the strain line for unbonded members, it looks sort of out of place. It's not linear. Okay. Now to fix this problem, what do we need to do? We need to bond these layers together. Once we bond it, then we can say, okay, the strain line now is linear, and we can apply the linear elastic analysis. Okay, and then we can say plane, the plane section will remain plane before and after bending, and we will get compression in the top fiber and extension or tension in the bottom fiber, and everything will look good. And we will also get this happy face uniform deformation. But we must make sure though that the stresses the stresses that are through this plane can be taken by the fixture or the bonded material that we apply. Now let's consider we now have a fully bonded beam, so we can treat it as one piece, and then we can use the linear stress strain analysis. Okay, if we draw the bending moment diagram and take a little length of dx, what we notice here is that when we take this slice out, the moment value on the left side is a little less than the moment value on the right side. Okay, so we can call this moment on the left side m, and on the right side we will get m plus a differential moment dm, so m plus dm. Then what tends to happen is we will convert these moments to normal stresses. Okay, so we have sigma 1 is equal to minus my over I, and if you guys remember, the negative value is because we've assumed that y up is positive from the neutral axis, and we will have compression or contraction at the top, and that's why it's negative. We did a video on the flexural formula, so you might want to go watch that if you're interested. So yeah, then the other side would be exactly sort of similar. We will have sigma 2 is equal to minus, open a bracket, m plus dm, y over I. And here, of course, the neutral axis in this case would pass through the geometrical centroid of the section. And I just left the direction of the moments here so you could sort of visualize what is happening for positive bending. But generally, when we draw the normal stress diagram, we kind of get rid of the directional forces of the moments. Now, let's see what's happening. We take this slice. Let's say we take a slice at a distance y above the neutral axis. Okay, or the right terminology is to take a free body diagram at a distance y above the neutral axis, and then study the internal forces within this section here that we took. What do we see? Okay, as we notice here that the sigma 2 is greater than sigma 1. So for everything to be in equilibrium, for all the forces to be in equilibrium, we need another shear stress, well, another stress if you like, acting in the same direction as sigma 1 to balance out the stresses from sigma 2. And this balancing stress is what we call tau, is what we call the shear stress, and that's why it's horizontal. Okay, and that's what we call the longitudinal shear stress due to varying bending moments along the beam. I hope it's kind of clear now. So if we have a beam, say for example, we have a beam with equal and opposite moments, the shear force will equal 0. The shear stress will equal 0. Okay, so far so good. Now look, then we convert these stresses into forces, and if you remember, force is equal to stress multiplied by area. So if we take a little area at a distance y above the neutral axis and call it dA, then F1, force 1, would simply be sigma 1 multiplied by dA. The same thing goes for F3 on the other side. We would have F3 is equal to sigma 2 multiplied by dA. Now, what would be the balancing force? Well, the area which tau acts on is dxb, where b is the width of the section at the location of the free body diagram that we took. And now, in this case, because we have a constant beam, a constant width b, so b will be the width throughout the entire section. And yeah, I think that's it really. I mean, that's really the end of the story. I mean, everything else is, I guess, you know, if you've understood it that far, if you've understood this far, then you've understood everything perfectly. Everything else is more of a mathematical problem, and it's just expanding formulas. We will go through it anyway. Okay, let's have a look. Now we have the forces F1, F2, and F3. So let's take sum of forces in the horizontal direction is equal to 0. Therefore, integration of sigma 1 dA, which is F1, plus tau dxb, minus integration of sigma 2 dA. So therefore, F1 plus F2 minus F3 is equal to 0. Then, yeah, we will just substitute the my over I in the sigma, so that will be integration minus my over I dA plus tau dxb minus, and then open a bracket, minus m plus dm y over I dA is equal to 0. If we expand everything out, we will get minus my over I dA plus tau dxb plus, because minus times minus is plus, so that's plus my dA over I, and they will cancel each other out, the minus and the pluses of my over I dA, and then we are left with, if we know our aim of course is to determine tau. You might want to maybe pause the video here to see how we expanded this equation, and if you get the same results that we do. So now our aim is to determine tau, therefore tau is equal to dm over dx divided by IB multiplied by integration of y dA. Then yeah, the dm dx, if you all remember the differentiation of the moment diagram is equal to the shear force diagram. Okay, the integration of the shear force diagram is the moment diagram. So we can replace dm dx with the shear force V, and the integration of y dA is the first moment of area Q. If you all remember, integration of y squared dA is the second moment of area. Okay, and replacing V and Q in this formula above, we will get the shear stress tau is equal to VQ over IB, or in some textbooks will be VQ over IT, where T and B are the width of the section where we are interested in calculating the shear stress. And the units for that is MPa, Newton divided by millimeters squared. The shear flow is simply Newton divided by millimeters, where we multiply the shear stress by the width T or B. Yeah, that's it. I think you will appreciate this formula more when we take it with the worked out example, when we use it more with the worked out examples that we will show. Yeah, so hopefully we will show maybe 3 or 4 worked out examples that may help you in future series. In the next video, just to give you a sneak peek of what we will talk about, in the next video, we will look at a 3-meter long wind beam in a residential building, and we call this WB1, resisting lateral wind loads only. We will ignore dead and live load. Now WB1 has been given to us as 2 laminated beams, and we need to work out the size and the spacings of the fixings required to unify or to laminate this beam, so that this beam can be one section. And we will do this using the shear stress and shear flow equations. Yes, hopefully it will be super fun. And I think this beam is set to bend around the minor axis, and we will also, we will work out the wind pressure as well, as per the Australian standard AS 1720.3. So please stay tuned. In the meantime, if you have enjoyed this video and found it useful, please consider liking, share and subscribing, so to encourage us to make more contents. Until next time, we hope you have a great afternoon.